All right, well, welcome back. We are moving along through Organic Chemistry 2 here for the summer. And we have basically finished the first two chapters, and we're moving on into the aromatics. We're going to be here for quite a few lectures, maybe 4-ish or so. We'll kind of see how that goes out. I kind of like to break these apart into bite-sized chunks so that you guys aren't sitting in front of your computer screen there for 2 hours at a time, right? But we are moving into chapter 17, and what we need to do, or what we're going to start out with, is just kind of introduce the idea of aromaticity. Now, as you guys have been going along already in organic chemistry and reading the book and watching videos and all this other kind of stuff, you guys have already encountered aromatic compounds. The quintessential example is benzene, right? I think you guys have probably seen benzene drawn a million times at this point, and at this point in your organic chemistry careers, everyone's really good at drawing basic shapes like triangles and squares, and especially hexagons and pentagons, right? And so when we think about aromatic compounds, benzene's kind of our go-to choice, and we've got our 6-membered ring, and we have our 3 pi bonds that are inside of there. Now, what I tell my students when we go through the first semester of organic chemistry is that this is, benzene is on a pedestal for the first semester. It's going to sit there and it's going to look down on us with its superiority, and we're not going to do anything to it, and it's not going to do anything to us, right? So we kind of leave it as a special group that just is kind of aloof and out there, and we're not going to do anything with it. The point being this. Right? We learn how to react alkenes in the first semester of organic chemistry, and obviously there are pi bonds within this aromatic system here, this benzene, but they're not going to react in the same way, although they do react in the same way. All right, and we'll get into what that means here. The point being this, all right? The point being this: when we want to react an aromatic compound, we have to put it under special conditions. There is a stability that comes along with being an aromatic compound. There's a strong stability that comes along with that. In fact, there's about an entire 3-ish or so pages in the book that discuss about that aromaticity and the stability, and they give you numbers, and they talk about heats of hydrogenation and heats of formation and all this kind of stuff that goes with that. So if you're interested in the numbers and all that kind of stuff, it's where was it, 17.3, I believe. No, 17.4, right? So if you look at section 17.4, they'll talk about all those numbers there and that kind of stuff. And that's not too important that you guys need to memorize the numbers. It's that you need to understand there is an energetic drive to form and maintain an aromatic compound. And that's going to be key, okay? So if you can form an aromatic compound, good, right? That's probably something that's going to happen. If you're going through a reaction and you don't have to break an aromatic compound, that's good too, because that's a high energy of activation and kind of, open up an aromatic system. And there's going to be a strong drive to reform it, okay? Now, I'm going to come back to these ideas when we start to introduce the first few mechanisms that we learn out of this, okay? So now that I've said the M word there, let me talk about mechanisms a little bit more. There's a grand total of 2 mechanisms that come out of these next 2 chapters. And if you guys have been following along and kind of keeping track on things, you might just say, well, geez, two mechanisms that come out of 2 chapters. Yeah, so organic chemistry 2 is a little bit different, right, than OChem 1. OChem 1, right, we have to lay a solid foundation and groundwork, right? We have to talk some of these core concepts like what are mechanism arrows and pushing electrons, and stability and intermediates and all this kind of stuff. And then once you have that nice foundation, then we can just build up on that, right? And so what we're going to see is that we're going to build upon those ideas again from OChem 1, there, stability and resonance and all this kind of idea, right? And we're going to apply this to aromatic systems. And essentially, okay, I paused there because I have to watch my words. Essentially, all these aromatic systems are going to react in the same way, okay? Now, again, if you guys have been following along, I rarely speak in absolutes when we talk about organic chemistry, because back when I was starting out being a professor, I kind of said the words always, and it's always going to be this way. And then quickly my students, well, what about this? And they found the the one exception, and then demanded points back, and then all right, fine, okay, whatever. So remember, what I'm teaching you is going to be useful for you guys for, let's say, 90% of the time, okay? Sure, if you want to go out there and dig it up, you're going to find exceptions and all this kind of stuff, right? And that's, again, great if if this is your major and we want to pursue this more, we certainly can, and it's important, all this kind of stuff, but right now, let's lay an important groundwork and understand how the vast majority of aromatic systems behave, and then we can come in and polish up those little details as we go through, okay? So, but before we get into the mechanism, let's talk a little bit about what actually is an aromatic compound, right? We have to define that. So the terminology aromatic, the story goes, as far as I understand, is that it was believed, right? It was believed that scents, right, smells, were all based off of aromatic compounds, right? They said that only aromatic compounds had a smell to it, this kind of idea, but that's clearly not the case. In fact, as humans, we're more attuned to carbonyl compounds. Carbonyls tend to be very easy for us to detect with our noses. That's not to say that benzene doesn't have a smell. In fact, you can go down to your local, hardware store and you can probably still find a can of benzene around. It was used as a paint thinner, as a solvent for many, many years until they discovered that it was particularly carcinogenic. And so then that was kind of phased out. But now you'll find more commonly something known as toluene, and toluene is very different, right? So here's our buddy benzene. It's got that classic solvent paint thinner smell, if you guys are familiar with that. If not, I don't really know how to describe it another way. And if we move to our buddy toluene, it's this. Wow. So we take a benzene and we put a methyl group on it. So it might be called methylbenzene, but it's such a common solvent, such a common thing. There's toluene. You guys, well, I don't think you guys are running labs over the summer. I was about to say you guys will probably use this in the lab, but oops. The times that it is, right? So if and when and however you guys are completing your labs for the summer, just pretend with me here at the moment that you guys use toluene and everyone's nodding on the other side of the screen. Great, okay. So a very, very common solvent that we use in organic chemistry, a high boiling point solvent, pretty useful. Now, here's the thing. Okay, so the word toluene, when we're talking about naming, is technically not a systematic naming system, okay? But this is such a common group and structure and moiety that toluene has become IUPAC accepted. And I saw this. Okay, so if you're looking on page 753, okay? On page 753, at the bottom, right at the bottom, there's a list, a picture or a set of structures that have all these common names with it. So toluene and phenol and anisole and aniline, benzoic acid, benzaldehyde, acetophenone, styrene. All those they're common names that we see over and over and over and over and over again. The reason why we have those is, again, because of very common structural features. And if we were doing this class in person, I would spend some time talking about each one of those. Just to kind of give a flavor for how important aromatic compounds are. Now, that's not to say that I'm skipping out on stuff with you guys here. What I mean is, again, I'm trying to keep these videos to a minimum so that I don't, have you guys, your eyes don't roll back in your head too often. You guys, not fall asleep here. But the point being, there's lots of common aromatic compounds that are used in everyday life, right? That you guys are going to see over and over and over again, and you've probably heard and you've seen and you might have even worked with and all this kind of stuff. And so that's why it's really, really important to know about aromatic compounds. Not only that, but there's a lot of the pharmaceutical compounds are based off of aromatic structures in there also, okay? So cool, that's enough of an intro for that. Let's talk a little bit about some chemistry then. Now, what makes benzene aromatic? What makes toluene aromatic? Well, there's essentially two parts that we need to pay attention to. To be an aromatic compound, right, you have to be a ring, okay? So you have to be a ring, and within that ring, you have to have a series of continuous p orbitals, okay? So now, be careful, I didn't say continuous pi bonds, I said continuous p orbitals. So you have to have, what I kind of simplify to say, you have to be a ring and you have to have usable p orbitals. So one ring, right, with, I'll put them in quote, usable p orbitals. And I'm being vague, and you guys can probably, like I said, if you've read ahead, which I hope you have, then you'll see what we mean by usable p orbitals here in just a second. And 2, we have to have a Huckel. I always forget if I spelled his name wrong. E-L. Apologies. So H-U-C-K-E-L. Huckel number of electrons. Okay. So there's basically our 2 criteria. Okay. We have to have a ring with usable p orbitals, and we have to have a Huckel number of electrons. So let's talk about the first part there. Well, to be a ring is a ring. I don't have to talk too much about that. You can see it in essentially any size ring, although, oops, sorry about that. We can see this in essentially any size ring, although the larger the ring system, the more complex this gets, right? You can also have this in polycyclic rings. So if you have a benzene ring that's fused with another benzene ring and naphthalene ring, right? We'll talk about that in just a minute. Then this holds true also, okay? The usable p orbitals, okay? So this is the key kind of maybe tricky part at the beginning. Usable p orbitals come in a couple different flavors. These p orbitals also have to be next door to each other, okay? So let's think here for just a second. I'm just going to draw an example, right? And this should look familiar to you guys if you've been following along with the lectures that we had. Okay, so let's say we have a set of carbons that are in a chain or in a ring, or whatever it is, right? So we're just looking at 4 carbons that are all bound to each other. And we've got a set of p orbitals here on each one of those carbons. And remember, just like we learned about in chapter 15? 16. I forget, I'm sorry. The previous chapter that we just finished here there with the conjugated systems. When you have p orbitals right next to each other, these p orbitals can all start to talk, okay? And that's the key part that makes something aromatic. We have to have p orbitals next door to each other. So we're bringing in we're bringing in ideas from that previous chapter there, where we talked about how orbitals overlap and the molecular orbital theory and the nice pictures in the book and all these kind of things, okay? Now we know, right? Now we know, for just a second, let me move these out of the way, right? Just for argument's sake here, right? And I'll just zoom in here, just so we're focusing on these 2, okay? Now we know that if we have a p orbital next to a p orbital, we can make a pi bond, okay? The reason why it makes a pi bond is because of we have the same shape and size of these. They can overlap, makes a nice bond. Things form a double bond at that point, okay? If we have a continuous chain of these, then all these are going to talk to each other. We're going to make a series of bonding combinations, all right? And that's going to be what's going to be talking in the ring itself, all right? So now let's take this idea and see how good an artist I am. So what I'm going to do, right? So I'm going to take, right, my benzene ring here, and if you can imagine, right, so if this is the plane of the board here, what I'm going to do is just kind of tilt this on its side. So we're looking at it, we're looking at it from this perspective here rather than on its face. Okay, so I'm going to tilt this a little bit here. And you can see this is going to be quite the challenge, but don't worry, I'm a almost professional. Okay. That didn't work as expected at all, but I think we'll get the point here in just a minute. All right. So one thing I've never mastered in all my years is quite being as talented an artist as some of my colleagues are. Hopefully you guys will bear with me as we go through, okay? So if you imagine we're kind of tilting this on its side, and in the back it's supposed to be further away and smaller as it comes. Okay, so really, for those of you guys who are saying, boy, this guy is terrible at this, I agree. But take a look at page 759. Here's what I'm trying to talk with you guys about here, right? So page 759. Okay, so there we go. So now what I did is I took the p orbitals that are available in each one of those carbons, and I just looked at those by themselves, right? So we got rid of the double bonds in there and we just kind of deconstructed that into the individual p orbitals. And so again, this goes back to the idea that we had in the conjugated, the chapter about conjugated systems, right? P orbital next door to p orbital to p orbital to p orbital, p orbital, right? These are all talking to each other. So all the electrons that are in these orbitals are all in one bonding combination. Okay, and then we can go up in energy and we add things called nodes and we create unique bonding combinations as we go up, and then we can actually construct the image that we have there with the Lewis structure. Okay, but the point being this, here it is. It has to be a ring, and we have to have p orbitals next door to each other. Now those p orbitals can come in the form of vacant orbitals, aka a p orbital that doesn't have electrons in it. Okay, so think a cation. Okay, remember, how do you make a carbocation? Well, you have to take electrons away from a carbon. And then its hybridization is sp2. And when you have an sp2 hybridized carbon, then you're going to have a vacant p orbital on there. Okay, and then we can use that as part of our aromatic system. And we'll show an example of that in just a minute. Okay, the other thing we can do is use lone pairs. Okay, now lone pairs come in a couple different flavors here. They're going to behave a little bit differently from what you might expect, but we're going to come back and we're going to explain this in just a minute too. All right. So for those of you guys who kind of zoned out, come on back here with me. All right. We need a ring with usable p orbitals next to each other, and those p orbitals can come in the flavor of pi bonds, carbocations, vacant p orbitals, or lone pairs. Those are the three things that you're looking for, okay? Which, at the end of the day, if you think about it, is pretty much everything, right? All right, but anyway, we'll give some examples that will clear things up, all right? Cool. So that's part number one, okay? Part number two is maybe the more confusing part here, the Huckel number. Now, Huckel number is 4n plus 2 equals your number, okay? So it's just a simple formula. Okay, so we have mathematical formula here. Some of you guys just cringed a little bit, that's all right, okay? 4n plus 2, let's just zoom in on this and think about what it is, all right? N is any integer value, okay? From 0 to technically infinity, okay? Practically, n is really not going to probably get above, I don't know, I think 6 might be the biggest limit you guys will encounter as you go through, but don't worry about that too much, okay? When n equals an integer, right, we get a number out of that, which is our Huckel number. The answer is the Huckel number, not the n. Okay, this is where sometimes things get tripped up. Okay, it doesn't matter what n is. Okay, the number here is what we care about. So, for instance, okay, let's say that I pick the number 1. Okay, so 4 times 1 is 4 plus 2 equals 6. That's what I care about. This tells me, okay, my Huckel number of electrons. And this number in here has to be satisfied within my ring in my p orbitals. Did you guys catch that? I have to go, once I calculate a Huckel number, I have to go look at my ring system with my p orbitals and count how many electrons are in there. So let's go do that. All right, up here we got our buddy toluene, okay? We are in a ring, and that ring, we do have p orbitals that can talk to each other. How many electrons are in those p orbitals? How many electrons are in those pi bonds there? Got 3 bonds. Every bond in the universe, essentially, right, takes 2 electrons, okay? So we have 2 plus 2 plus 2. So 2 plus 2 plus 2 is 6. Is 6 a Huckel number? Yes, it is, okay? So toluene satisfies our 2 criteria. It's a ring with usable p orbitals, and within that ring and within those p orbitals, it has 6 electrons. Thumbs up, we're good to go. It is a aromatic system. That's the name of the game, okay? N It has nothing to do with how many atoms there are, how many pi bonds, how many lone pairs. It's just an integer. Pick an integer, plug it into the equation, and this is the number that you care about, okay? So for instance, okay, let's go crazy, and instead of picking 1, we're gonna pick 0. Wow, okay, I know. 4 times 0 is 0, right? So our Huckel number here would be 2. Okay, so now, right, we can generate an aromatic system with only 2 electrons. Oof, that's tough, okay? But that actually is something that is real, right? So here is our example for an n equals 0 aromatic system. I have a ring. I'll put a, you know what, let me put this in green here. There is that. So here I have a usable p orbital. Here I have a usable p orbital. I don't have a usable p orbital yet at this carbon here. It's sp3 hybridized. All my p orbitals are hybridized. It's getting, right, there's no way for these all to talk to each other. But if I generate a carbocation at that carbon, okay, now I've got usable p orbital, and a usable p orbital. So all my, right, my ring has all usable p orbitals, and if I count 1, 2, I have 2 electrons within there. Okay? So this is an odd example, but a very common example of an aromatic system. All right? So notice that I can use a carbocation, since it has an open p orbital, to make my continuous system of usable p orbitals there also. And the same can be said with negatives, okay? And so we'll give you an example of a negative here in just a second. But so any integer value from 0 up to infinity, if n equals 0, then we have to have 2 electrons, and there's our example of that. To be honest, I can't really think of another example where n equals 0, or our Huckel number is 2. So really, I think this is the only one that we've ever seen, and to be honest, we don't deal with it too much, right? It's just kind of one of those examples we give when we're introducing this topic, okay? So let's give another example of n equals 6, right? So if we are 4n plus 2, right? If we give n equal 1, right? Then 4 times 1 plus 2 equals 6, right? So that's not to say that 6 is only equal to benzene. Any system that has 6 electrons in a ring with usable p orbitals will be considered aromatic. Benzenes are most common go-to, okay? But let's think of another one. 5-membered ring, okay? Sounds good. It is a ring. I will give it some usable p orbitals. Pause, okay? Pause right here. Is this a continuous system the way I have it drawn right now? Okay, so pause, take a look at it, see what you guys can come up with, okay? So we have a ring. This has a usable p orbital, usable, sp3 hybridized, right? So we break that right there, okay? They say, aha, Dr. H, I know, I just learned a cool trick. I can put a positive charge on that ring, make it a carbocation, and then I have a continuous system of p orbitals, and you would be 100% correct. That can all talk to each other there, right? These can all talk to each other right there. But is it aromatic? Got it? How many electrons are in that system that I have drawn right now? Okay. Well, let's count. 2, 4, and that's it. If you're a carbocation, right, you don't have any electrons there, right, so you can't count anything from that. So I've got 4 electrons in a ring that has a continuous set of p orbitals. Does that make this aromatic? Well, no, it does not. It only satisfies part of the criteria. Can I make any set of my Huckel equation here equal 4? Well, 0 is equal to 2. If n equals 0, it's equal to 2. If n equals 1, it's equal to 6, right? And I can't do halves. They have to be integer values. So the answer is no, okay? So this is not an aromatic system, okay? This is not an aromatic system. All right, so, and if you take a look, there are a couple other definitions. It's aromatic, non-aromatic, anti-aromatic, right? All this different kind of stuff that's in there, all right? But we'll deal with those at the moment, okay? We'll deal with those other ones at the moment. So there's that. So let's make this aromatic. Now I can play my second trick, right? I can make that into a negative charge here. All right. So here's where we get into something that's a little bit unusual, right? What might happen here? Well, let's think for a second, right? Let's go through the obvious and then we'll tell you what happens. Now, we have a ring, usable p orbital, usable p orbital, usable p orbital, usable p orbital. Where's that lone pair sitting? Well, that lone pair is sitting in an orbital that has p-type symmetry. Now, if you guys just listen to what I said there and said, what in the world is he talking about, then don't worry. Here's what I'm going to say, all right? Let's simplify this idea. If we get rid of this idea of symmetry and overlap and all this kind of stuff, can you draw a resonance structure with that lone pair, okay? And the answer is, well, I can, right? Let's pick this, right? Okay, I can draw that resonance structure there. And if I'm following along, I can do this. Let's see, this was green then, right? And then this was going to be black. Cool. Why can you draw a resonance structure? Why can you draw a resonance structure, right? Well, the reason is why, because the symmetry here, this is what's going back, right? The shape of this orbital is the same as a P. And so then we can use that to overlap. That's what we're talking about with symmetry. It's just, are things looking the same, okay? Now, when you guys go on to inorganic chemistry, you guys will talk more about symmetry and all these kind of things. And then that'll make more sense there, right? So in a year and a half, you're gonna be like, yeah, I remember that weirdo, we talked about that over the summer, right? Symmetry is cool, okay. And that's gonna explain a little bit more about what we talk about here, all right? So we can use lone pairs as part of our continuous p orbital system here. Is it technically a p orbital? No, right? But that's okay, right? We can always fudge the numbers here a little bit. Why, though? That's an important question. Why am I going to be allowed to do this? Watch. If I count this as part of my aromatic system, okay? So now I have 1, 2, 3, 4, 5, 6. Is 6 a Huckel number? Well, yes, it is. And remember what I said at the beginning of all this long rambling here. There's a strong drive to make aromatic systems. So what's going to happen is this molecule is going to kind of, it's technically speaking, it doesn't really want to, it wants to be sp3 hybridized, all this kind of stuff, right? It's going to want to overlap and have all these orbitals talk with each other because it then forms an aromatic system. And that's a very stabilizing effect, okay? This is our buddy cyclopentadiene, right? Cyclopentadienyl anion, a very, 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 very common anion that's used a lot. It's particularly stable, right? We can make some really cool compounds in here. There's some very pretty colors, yellows and blues and reds and all this kind of stuff. So when you guys get to inorganic chemistry, you'll definitely see this one again, okay? But this is an example where we can see a negatively charged carbon that will drive to have its p orbitals overlap with the rest of there to form an aromatic compound. And it will do that to form an aromatic compound. That's kind of the reason why, okay? So with me on this one, we can use negatives, we can use positives to drive to form an aromatic compound is what it is, all right? Fantastic. One last example I wanted to talk about here is another very common aromatic compound. I'll go and tell you that it's aromatic. And I'll do some color coding here. Let me go back and make these green, and then you guys will get the point, hopefully, or it'll make it a little bit easier. So let's zoom in here. Here we have our buddy Pyridine. Pyridine sinks like crazy. It's a very common organic base. Especially when you guys go on to the biochem, you guys will see pyridine quite a bit in there. I think it's used as a solvent for, I forget what exactly, but I just remember walking by the biochem labs here, and I could tell the days when they're using that in lab, just because it just reeks out in the hallway there. But anyway, we have a ring. I didn't say the ring had to only contain carbons, did I? No, I did not. Right? It said it just has to be a ring. It's not exclusive to carbons. So we have a 6-membered ring. Does each one of the atoms in the ring have access to a usable p orbital? Well, double bond here, so yes, 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 yes. Okay? How many electrons are within that usable set of p orbitals? Well, 2, 4, 6, right? So again, we've satisfied a Huckel number. So it is a ring, it has usable p orbitals, and it is a Huckel number. Good, it's aromatic. Question then, right? What about those red electrons right there? Well, here's the thing, right? So again, I will point you to page, I'm looking at page 766 is what it is, 766, right at the bottom. This lone pair, right, if you think about this, right, now here's the key. This ring right here is completely flat. It's a completely planar ring, okay? So if I try my best to kind of draw this on its side again, right? You know, maybe I can do this, right? So imagine that's going out into the back here, right? Can you guys kind of, hopefully you guys can follow along with this. Let's make this, let's see, if let's make this in purple here. So imagine right there's my my 5 carbons, right? So I'm kind of looking at this from the side. These are my pi bonds, right? They're sitting above and below the plane, okay? Right, so imagine there's a cloud of p orbitals sitting above here, right? And there's the corresponding secondary lobe, right? So we make the sandwich of pi electrons here, right? Since this is planar, okay, and because that then this forces the hybridization here, right? So what is the hybridization of this nitrogen? Well, you could go through and right there's 1, 2, 3 bonding regions, so it's sp2, right? So it's trigonal planar. All the bond angles in there are about 120, okay? Which means that red set of electrons, right, are sitting in a lone pair that's sticking out, right? This is not able to overlap with the rest of this ring, okay? It's pointing in the opposite direction, okay? So if we want to kind of color code this a little bit more, right, essentially, right, there's a 90-degree angle between the pi cloud and that lone pair in there is what it is, okay? That's what's going on. It's sticking out, it's orthogonal, it can't overlap with the rest of it in there is what it is. So be careful, not every lone pair can be part of the ring, okay? And this has some unique properties to it, which makes pyridine extremely useful and all these kind of things with that, all right? Cool, so I think I've kind of talked your ear off enough at this beginning part here. This is a good intro to what makes something aromatic. Some fantastic examples in the book there. Go through, see if you guys can pick out what is aromatic, what isn't. I promise, if you spend 10 minutes looking at some of the examples, you're just going to be able to start recognizing this stuff, okay? I should have just started this whole out like that. It's like, okay, go look at the examples and I'll wait here for you. Okay, but anyway, please go look at those examples. Please email me or whatever you need to, get in contact with me with whatever you need to, and I can walk through this stuff with you guys if you're having trouble with it, okay? But I'll be back in the next video. We'll continue on with 17, and we'll start to get into one of the first set of mechanisms with all this. All righty, well, have a good rest of the day, and I'll see you guys.